Okay, hello everybody. Today I will speak about quantum chemistry. It's the work that I'm making with Chi and with Alejandra. She, and Alejandra. And okay, let's start in for the first part to stay everybody in the same point. First, I will speak a little bit about variational quantum eigensolvers and in molecules. The variational quantum eigensolvers is a really hybrid algorithm that is really simple, that is divided in two parts. The first part is the state preparation. You start with a reference state. This depends on the problem, and then you pass this state through a parameter size circuit that depends on a lot of parameters, and you obtain the final psi, the final state. Here you start, and you pass through the layer, and you have the psi, and later you make the measurements. The measurements can be the magnetic momentum. Normally it's the energy, and for our case it will be the energy. And normally you measure the project measurements of your state. For our case, we will work in molecules. So this circuit, the circuit we will use, will be the unitary coupled clusters. That is something that is based in the classical chemistry, and what is have this form. It's the exponential of the t minus t to have unitarity, and the t is made using the ladder operation and is to construct the molecule. And this is the first order and the second order. It's what is called second order quantization. You can put a lot of terms, but with the second, it's a really good approximation, and you can stop there. And later of this, what you make is measure the energy, and you measure with the projection of Pauli, and then you parameterize these measurements with some parameters that are calculated using the second order intervals. Here, everything is classically. What you make in the VQE is you pass here, you make the measurements, you have the energy, you minimize, you come back, and you make this layer a lot of times until you converge to the search value of the energy.
Julian, if I have question, I can interrupt you or wait until the end.
What question you have?
The parameters that you put inside the operation and blah blah blah, they are computed classically.
Yeah, here what you make is you prepare the quantum state with the variational circuit, and here the unitary coupled cluster. And later you make the measurement of the energy, and you get the energy of the system. These parameters are fixed parameters that you can calculate making integrals. And then you have the energy, and you derive, and you see you minimize this energy. So you recompute the parameters that you put here, and then you come back and you make it until you find your search energy. You repeat this process. It's like in Kuwawa, or like you minimize. Tell me, Javi.
So you have to measure as many times as the number of observables that you have, because each time you introduce a different.
Yeah, normally what you make is like these parameters, you search the computation, and you make for example, you can measure all this Pauli operator, and then you can sum all the energies. Like this is like you measure this, and you sum all the energies, and you got the final energy.
Okay, so that is the point in which you have the advantage.
The advantage is that you have all the information on this state, and you store all the information. You have all your state here. So it's easily to compute this, and then you can when you make the measurements, you can make a lot of measurements.
Yeah, but I mean, the advantage with respect to the classical counterpart, in the end, if you are encoding that in a parameterized quantum circuit, it is the same that storing the angles. So as far as you have a polynomial quantity of angles, it is the same to prepare the state. So where is the advantage with respect to a classical model?
The advantage is that when, for example, you have not, later there is some adaptive, like the adaptive VQE that you don't need to find the perfect VQE, the perfect state. You need a good state. So if you don't have to optimize all the parameters, there are some variations that you only calculate some parameters like the adaptive. So you find you can find a minimum, but maybe not the exact state, but something good enough. And you store all the information in this state. So you can move this state, and if, for example, if you have the parameters, then you can measure other quantities. So
I was late. So this U is the proprietary associated plus Hamilton, and will be something totally different.
This is the circuit. This is this circuit.
But that circuit doesn't reproduce the dynamics associated to this Hamiltonian.
See, this circuit is this quantum coupled cluster that these have the information here is the information of the molecule in our case.
Okay, so the idea is that you have to
You encode the information in the circuit using unitary coupled cluster, and then you optimize this, and you get the final state. And with this final state that you calculate with the unitary coupled cluster, you work with it.
So in principle, that the state that you prepare could be entangled, right? So you are looking for a minimum, probably.
Yeah.
Then that's advantage. Typically, to create that state, I mean, it could be a state which is pretty entangled, right? So,
Yeah.
And then, so you cannot create that entanglement without.
Yeah. Normally there is entanglement. Yeah.
So you need a quantum circuit to create enough entanglement in case let's say the state with less energy is entangled.
Yeah, the advantage is to store a quantum system in a quantum system, and you have all the properties, because you can make, when you make the transition, when you calculate the Bragg-Kitef, or you transform your molecule, what you want, or your solid state, your quantum stuff, with using Bragg-Kitef and everything, you have the advantage of store quantum stuff in quantum stuff.
No, yes, because I want to answer Carlos, Carlos Javi, so if you first. No, you don't know the ground state, so you cannot prepare it.
When you optimize the parameters to get an approximated ground state, the information that you are encoding are the angles. So if I store the angles classically, I have the state.
Yes.
So there is
But you are getting.
an advantage because
No, the problem is not there. The problem, the advantage is that you have to measure. This is because VQE has not a quantum advantage with respect to classical.
so the advantage is when computing the expected value of the Hamiltonian.
The advantage is because you compute expected value faster in theory, because you have to recall the information.
Yeah, because here you can measure all at the same. Here you have the projection of this. For example, when I was playing the hydrogen, you can see easily, but you have here the Pauli projection. You can measure all the projections at the same time.
Yeah,
For example.
the problem there is that to compute this classically is quadratic in the size of the matrix, right? However, if you want to estimate the mean value, this is also quadratic because you have to make an average.
Yes.
So in time, VQE has not advantage, but it's the only way that we have in order to compute energies or eigenenergies of molecules. So there is no proof of advantage, is what I mean.
Yeah.
But the problem is not in the preparation, as Javi was asking, is in the measurement. It's very slow.
Yeah.
So typically it's in U, right? So this U codifies all the parameters, right? And you generate an state through some propagator, and then this needs to.
I think.
This U generates some,
some
dynamic.
I think will be easier.
Imaginary time evolution. So it's a cluster state.
I think will be easier when the hydrogen molecule. Like later we will work in the hydrogen molecule in this and this example with the shortcut and everything. I think, I don't know. We can continue here discussing, but.
That's one point. D is a Hermitian, not anti-Hermitian. So this is not a unitary evolution.
This is unitary. Unitary coupled cluster is the name. It's unitary because because this is classically you make this, but here. Yeah, it's the angle. Here's the angle. Here because here you can make if you make it for example for the adiabatic stuff you don't have the angle here, but later we put here the angle because later this is the angle. This is the angle that you can change, and then you subtract this with the other, and you have there that. This is what you optimize. Okay. The problems of the VQE. There is two big problems. The first one is how it scales the ansatz. Normally, the ansatz scales when you make you take your molecule and you pass to the quantum circuit. It scales with the Bragg-Kitef and the Jordan-Wiener. It scales really bad. For this molecule, this is really simple. It's 110. So finally, you are arriving to an optimization problem. So if you want to make something more interesting, like a bulk or a benzene molecule, maybe when you calculate the terms of the Hamiltonian is huge. You have a huge problem with a lot of parameters. And the other problem is the Barren plateau. The Barren plateau are when you are making the optimization of, you can imagine that you have a manifold of n dimensions, that all n dimensions are all the parameters you have to optimize. There are a lot of areas that have a gradient, really small gradient, so when you are making the gradient descent, you get stuck there and you cannot exit, so you cannot find the optimal minima. So we are going to try to solve this problem. For the okay,
I have a lot.
tell me.
Just one of them. When you codify the state of the molecule in the qubits, what are you codifying exactly?
You have the Hamiltonian. That is the Hamiltonian. You have the cinetic term, the nuclear, nuclear electron, and electron. This is your information. And there are fermions, and you're codifying in fermions. So there is the Jordan-Widner and the Brady-Kitev and the parity transformation. What you make is you take your system with a ladder operator, because you can write everything with ladder operators, and you put it in the qubits. Yeah. This is how you codify. So for some with Brady-Kitev or Jordan-Widner or parity, there's a lot of options. That depends on your problem. You can use one or other, and they are much better because it scales better. For example, for the hydrogen molecule, if you use Brady-Kitev, you only need 2 qubits. With the Jordan-Widner, you need 4. So there is that one, and the number of terms. There is not, but it depends on the problem. Okay. So let's start with the problem of the baryon plateau. For the baryon plateau, what we propose is like we propose to use particle swarm optimization to optimize this problem and try to evade this small gradient areas. The particle swarm optimization, what you make is you put a lot of particles in your manifold. You have this. Imagine that this is the answer that you want to optimize. You put a lot of particles, and they start to search his own minima, and they start to search. But they have a small communication. It's not like gradient because in gradient you have one point and search their own minima. Here they can speak. It depends on the problem. Everybody can speak, or maybe someone can speak. Is one with a neighbor. It depends. So there is a part that you start to optimize your own minima, and they start to speak, and they finally achieve to a good minima. Maybe not the best, but it's a really good one because you control all the area of your manifold. Here you can see how it works. You have your position, and this is the position of the next step, and this is the velocity. And the velocity is where everything happens. That here you have the inertia, this is the velocity of the last particle, and then the global part and the local part. The global part is the ability to speak with other particles, and the local one is the ability of search. And you can change these parameters, so you can make first, for example, you can make that all the particles, they start to search, and they are by itself, they don't speak with together. And when they find something, when the number of steps is much higher, they say, okay, right now start to speak. So what happens is that they start to search, and they start to converge all to a minima. So in this way, you cover a lot of part of your manifold, and you don't get stuck in low gradient parts, like in your baryon plateau. And now the other part that we want to treat was how it scales. For here, we are going to use shortcuts. Shortcuts, to explain, we make a really small summary, because when shortcuts here is, everybody knows. Shortcuts are fast, not adiabatic. Dime.
Sorry, I actually didn't understand how you solve the baryon plateau problem with the manifold thing. I mean,
but imagine
you face the same problem.
Yeah, the same problem. The thing is that imagine that you are here. So imagine that you are only one. This is the gradient distance. So you start to search, and maybe you stay here. You cannot see this. So you start to walk here, and you don't find anything because you are working something that you don't find anything. There is not gradient. You get stuck. But maybe if you put a lot of particles, and the one go to one direction, the other to other direction, everybody goes in one direction, and they, for example, have a telephone. They can say, okay, I found something, and they go there, and they start to search there. It's like divide the problem.
Okay.
So you don't, because
and this communication is done with these terms that you show there.
Here, this term is the global term, that is the communication between particles, and this is the search of is on search, the local part.
And it is codified in. I mean, because I don't see exactly what.
X is the global term minus the position. This is the best position minus the position of the on part. This is the best that you when you compute.
I mean, how do you put that information? How do you, because they don't have phones for sure. So how do these molecules communicate?
When you measure, you get the best value. So this is in the classical way. That is, if you optimize this particle swarm, classic particle swarm, what you make is this: you measure and you get the best value. You measure. So you get all the values and say, okay, this is the best value, and you imagine that you are the particle. So you say, okay, The particle 3 find a good value. But this is the difference between the best value and your value. And here is the weight. It's like, okay, I don't want to go there. If it is very high, you want to go there. If it is very small, you don't go there. I say, okay, I continue searching my own minimum. I don't care about the global minimum.
Okay, I get it now. Thank you.
Okay.
Maybe one question related with this, because when you do the gradient descent, you are having only one particle which is trying to search for the minimum. But here you have many particles, so each of the particles has their own VQE circuit and measurement.
When I codify this, I make this. But I think will be more interesting, but is to use the entangle, like when you make the measurements, maybe to codify the global term, maybe you use the entangle or something like this. Use quantum nature, because if you you have to make measurements of one part, you can divide the problem. You can use entangle and use the advantage of the quantum stuff. But what I make is make a lot of measurements right now.
How do you change the phi functions in terms?
This have, if I don't remember bad, it have like the acceleration. Like you can divide this in acceleration another term. The term I think was the position or something like this, or the time. So normally what classically is done is like you start with this in a value, in a high value, this one, and this in a small one. And when you are making the steps, for example, at the half, they are in the same point and they are changing. So the number of measurements you make, you start to change the value of this.
So it depends on k, not on the value of the function.
This depends on the k. Yeah, normally yes, but you can. But I think you can relate it also. I don't remember, but I think you can relate it also. Because this you can decompose in acceleration plus something. I don't remember what is something.
However, the thing of making phi depend on the actual function can be a problem for the convergence, because particle swarm optimization have a very narrow convergence.
Yeah, you have to mind it.
So it's difficult to make personalized tuning of the parameters, because you risk to lose convergence.
Yeah, you have to study the convergence. There is like, if you see the parameter, there is only one small plus of the convergence, and the rest is no convergence.
Yeah.
But you have to choose, like all the gradient descent and everything, you have to choose well your stuff. But the thing is that you measure a lot, and maybe if you use, this is one idea I had the other day, maybe you can really.
Additionally, which is the advantage with respect to gradient descent starting on?
That you don't get stuck.
No, so the way in which you prove numerically that something is irrelevant.
Because if you have the communication, that it's like if you make a lot of gradient descent, imagine that you have this gradient descent, no? This, and you start in a lot of points. You don't have the communication with another particle. So the advantage is that if one find a good minima with the global term, you're going to go there, and you're going to find first you're going to find a good minima, and then you're going to make like a precise measurement of the minima, because a lot of particles are searching there. And it's not a bad method. Like classically, is very used. Well, you make the master, you make the subject of this.
So what's the difference if I just do like normal gradient descent, try a lot of initial points different, and then I take the best one? How is this different?
Because in the gradient descent there are independent measurements. Here you have connected measurements. So if you have a gradient descent here and you don't have communication, maybe it goes there and it loses. And you can start here and goes to other way.
Okay, so the idea is to do this in a quantum way, and then you only have to do one step.
No. Well, I don't know. This is quantum swarm. This quantum particle swarm is done, but I'm not an expert. I have to read about it. But the idea is that if you only make gradient descent, you lose a lot of points, because it goes to one part, it gets stuck, it loses it. But if they are connected and they can speak, then this point doesn't going to lose. Like they are going to go together finally, because they all go together to the same point.
I don't care about the points. I only want to know which one is the best.
Yeah, but finally when all goes here.
Yeah, but the same with gradient descent. If I just try
No, but here later with the local term, or when they start to search there you cover with all your points this zone, and then you optimize this zone really, really good, because you have a lot of particles in this part. You don't have here, because if the valence it goes here, you lose 1 point. You lose a measurement. Okay, and now the shortcuts. I will start because I don't remember where I finished the shortcuts. So shortcuts are fast route that follows non-adiabaticity, but what they want to make is make fast the process, but don't lose the properties of the adiabatic process. Adiabatic process, to make it really, really slow, and what you make is that your state doesn't change and is always in the ground state. But you want to make it fast, so what you make is control the parameters of their system and force to your state to live in this one. Like you move the parameters, you change the parameters in a way that your ground state stay there, live in the, your state lives in the ground state and don't go to excited state. There's a lot of way to make it, but I'm going to focus in the counter-derivatic, is what I will use later. The counter-driving, what you make is you have your Hamiltonian, this is your original Hamiltonian, and you add a counter-diabatic term that what makes is this, is force to the Hamiltonian to stay there. Also, to find counter-diabatic terms, there's a lot of ways to find it, but I think it's really illustrative and you can see really what the physics if you look in the gauge potential theory. This is proposed by Demi Planck and S. Rice in 2003, and they suggest that maybe that you can use the gauge infinitesimal generators of unitarity as the connecting terms. Is that you put here this term. This term is composed by the variation of your the derivative of your parameters and the gauge potential. The gauge potential. And the gauge potential is the term which forces to live in the diagonal, that the Hamiltonian is diagonal and don't go to excited states. And it's really is connected to the generalized force. And to see an example, is classical example, imagine that you have a moving framework, this is your system. So if you put a ball here and you want to follow this straight line, there is some force that appears in the because the framework is moving. For example, the curl is 4. So what you make is add a term that have the same structure but in opposite direction to force to the ball to follow and don't be affected by the Coriolis force or the generalized force. Okay, this is very beautiful, but how do you connect the gauge potential? You can connect it, you can make it in 2 ways. Using the Berry's corrector, or, well, there are a lot, but I will focus in 2 ways. Using the Berry's connector and the least action principle. Like this is an adiabatic process, and adiabatic process is studied a lot by Berry. Berry study how it have to move, the correction, the geometric phase, everything, and you can connect your gauge potential, you can calculate it using this formula. What happens? This is exact, this is wonderful, but when you scale your system, this have no solution analytically, or it's really hard to calculate. So here we can use also the least action principle. There's a minimization, you can minimize and find a good enough gauge potential. These are exact equations. Here you have your Hamiltonian, this is the generalized force, and this is your gauge potential. And you know that if this is true, so you can find this. This is like Berry's equation, that is mathematical of Berry. So you define this one, and you can define a function that depends of how do you chase A, and this is your approximate one. So what you make is you use the nested commutator to generate the structure of a good gauge potential, but you don't know the parameters, but you find the structure, and then you put it here, and you find the minima, you find the point when this is 0. And how do you make this? Using the Frobenius norm. So you minimize this one, and you try to find that when this and this are the same, when this equation is true, because this situation is this gauge potential is the same, is the correct one. If this approximation, this is not equal, it's approximate. So you try to find this to optimize this, and you can find the minimum optimizing these parameters in this equation. Okay, now that more or less you understand shortcuts. Shortcuts is made by Chi.
I have a question.
Okay. Jeje.
Sorry. And which
¿Dónde te has
of
quedado?
the
Where? Where is the question?
no, no,
Here.
on the shortcuts, I mean, you explained perfect, I understood, but I have the question of which of the two problems that you said at the beginning does the shortcuts solve?
The shortcuts,
The
what?
plateau, the ansatz,
The scaling of the ansatz. I will
and
explain it
how
now.
and why?
It's here explained.
Okay.
It's explained because the QAWA that Pranava make it, here you can see the good advantage. Here, digital, the idea is to put the structure of the shortcut in the digital circuit and see if the shortcut also, well, we know that the shortcut also help to find or to speed up the process. For example, in the QAWA, when you are working with QAWA, you have these circuits that this circuit have like local rotation and a global rotation. And you make the same that to VQE. You start to make a loop and you start to optimize, until you find a good enough a good net measurement. What we make? We add here the shortcut term, this is the shortcut term, and we make everything but adding the shortcut. And for example, there is an experiment, they make the simulation in a mixed field spin 1/2 Ising chain, and they find that if you want to find the ground state of this Hamiltonian, you have to make an optimization of 2n steps. N is the number of particles, but if you use shortcuts, you find you only need 3. I think that, okay, normally what the people say, no, it's because you have more parameters that optimize, but your result is much better. So maybe these parameters, you have to optimize more parameters, but also they are good parameters to optimize. Like they give a really beauty operators that, and with these operators you can find your ground state much easier. And our idea is to make the same. Here you have the UCC SD circuit I explained before. So you have here the shortcut, and this we will speed up. We think we will speed up the VQE process because you are going to have the Hamiltonian. You will have some terms, and these terms make that the number of loops that you will make will be less because they are really, it's like well-chosen operators. Okay, and here there is a small example of the region that we make. Here you have we codify you have, okay, because maybe I have to explain it better because maybe you have your Hamiltonian of your molecule and you transform this Hamiltonian you can pass it to this, and like you can speak in digital computers. Like you pass from your Hamiltonian to this, and you use here, for example, the Rayleigh-Kittev. So you pass from the real Hamiltonian to the quantum state. And this probably what you make here is that you are turning on the interaction between electrons. You have here your initial and well-known Hamiltonian that is without electrons, and you can find really easily is this part. You can find really easily the ground state, and then you turn on the interaction, and you go to the final state that is really crazy. So what we make here is use the nested commutator at first order to calculate the CD term. So now we put this CD term here, and we get the complex unitary coupled cluster second derivation shortcut. This will be this. And what we find is that when we optimize everything, we find really fast the minimum. This is comparison about adiabatic, the shortcut adiabatic, and the VQE. Okay.
How did you get those specific numbers?
These numbers. This is first you have to calculate the second order integrals that are integrals. Integrals, there are some programs, and later you have to pass from your interaction of your leader because you can write the Hamiltonian, you can write it in second in leader operators A, AI, and this with the parity with Jordan-Wigner with the Rayleigh-Kittev as we use here, you can pass from here to to this one. Well, to this Hamiltonian.
Okay. Giancarlo, have you finished?
Sí, creo que sí. No? Do you finish, Giancarlo? Ask Mikel.
Yeah.
No, tell me.
Then, maybe I'm missing something, but then it's not work.
No, it goes here because I didn't, because I was find later, it have to be 1.13, 1.3, no, this is the VQE, and it goes in the fourth step, it goes to the exact point. Your energy, you're comparing between the energy, exact energy and your VQE energy is 0.99995, something like that.
So, but what I mean is that then the result with Sorkat is the worst one.
No, it's the best one because this is the exact one. And this the VQE is this one, so you find the exact energy. STA is VQA plus STA. STA is the, because here is compared if you make this with adiabatic transition, and adiabatic is not VQA, it's other measurement. Like, it's not a comparison between VQA and VQA STA. I have to make, what I say, I have the programs, I have to make the metrics now, and this is the results I want to get now. That it finds the problem is that well, here's the conclusion. The problem is that we are working now with a small molecule, so the VQE works perfectly, the gradient descent works perfectly, everything works perfectly. So the thing what we are making now is go to a bigger molecule, the lithium. We are making the lithium. We are calculating the shortcut now. So because when you start to make bigger the molecule, there is where it should works better.
Maybe you can also do another thing, which is to compute the higher eigenstates. I think this will be the same size of the model. This will be.
Now the thing is that if you, for example, to compute, and this is also a problem because, well, it's not a problem, but right now, the particle swarm optimization, I make the calculus and I optimize really good the system. I use it and I'm making the Qiskit and it works really good. What happens that the gradient descent works also really good. And I don't know how to make the comparison, so my idea is to go to a really complex molecule. The lithium is, I think, is complex enough, it's 100 parameters, to see if the other gets stuck, is big enough to get stuck, and the particle swarm optimization goes to a better minimum.
No, but what do you mean? Even with a small molecule, you can also compute the eigenenergies.
Yeah, okay.
And this problem is much more complicated because you have to subtract.
Yeah.
It's complicated.
Okay. Yeah.
I have questions.
Wait, Carlos is with the.
Okay. I listen with you.
I don't know if you were asked this, but I am confused because I think the last thing you explained is like adiabatic computing, right?
Adiabatic computer, and I have the thing is that here I say.
VQE, right?
No, but I calculate VQE STA. What I have to make now is, because VQE go to a bigger molecule and make a fair comparison and compare.
This was not VQE, right? This was like, because you are not doing like, okay, I try an answer, I classically optimize parameters, you are doing like a continuous change.
No, here no. Here, if you, these parameters, what you make is you go here. This is, imagine that this is a seed gate, this is a double seed, this is a X, and then you make the measurement. The measurement that you make is with these parameters. You make the measurement with this that you pre-compute with the integrals.
I think Carlos saying right. So you mix the two things. One is adiabatic algorithm, and the other one is VQE. I think Carlos' question is more relevant to your time-dependent value. For VQE, you don't need. For adiabatic algorithm, yes, you need a reference time evolution.
What we make is that first we calculate, okay, here this is the time dependent because we calculate for the adiabatic one. What happens is that later you don't need the time dependent because you optimize these parameters. I don't know if this is the question you are making.
How you choose the lambda?
This lambda?
No.
This?
Yes.
This is the lambda, the scene, the adiabatic typically, because what you want is find the structure of the CD term. Later you optimize the parameters.
No. Then you mix the two things.
Yes, you are going to the ground state of H0, right, which is easy to compute, and then I guess you're slowly changing lambda in order to get the ground state of the.
No, this is how, okay, this is when you make to adiabatically, no? But what happens that you want to calculate the CD term. To calculate the CD term, what I make is I take this structure.
Yes, but you classically do that, and then in shortcuts, what you do is to compute some term, the CD, and then you can do it faster, right? That's kind of the idea. But if you are doing this, you are not doing VQE, right? You're doing adiabatic computing.
No, because in a diabatic computer, well, later you have this structure, and you optimize only this parameter, and you have this parameter, and you have this, and you make a transition.
No, I think like you have to change the presentation.
Okay.
I think at the beginning there's two strategies. One is adiabatic combinability, right? You change the lambdas and you calculate the CETN. Somehow you speed up the adiabatic evolution. But he wants to present is that okay, at the beginning we have the Hamiltonian, no matter how the time evolution it is, but you always can calculate the CETN, and you just take the structure and to put the VQE to calculate again.
Yes. I don't know if I missed your question. I think I did this, but I don't know.
You have to separate this.
Yeah, I think maybe.
Why is that?
Later we talk because I think I don't get in your point.
Now I am more confused.
Ask Anna or no.
Okay, thank you. In the final plot, I didn't see which one is better, but also which method do you expect to be?
This the
better?
red one is the.
This example, which is so simple.
This is the VQE method, the blue one. I don't know if you see. What is your?
Yeah, so the best one, right?
The best one.
The
Yeah.
one that reaches fastest.
Yeah. No, better, not faster, better, because there are only 4 steps.
And is the VQE like pure VQE? So
No, VQE
without this optimization that you included and you mentioned, or with?
No, without PCO. PCO is I will making the measurements in other. I have to put the thing is I didn't put everything together. I have to make the metrics now.
Okay, and also this result is without taking into account noise or whatever gets involved in the process, right? It's simulation.
Yeah, simulation.
Okay, and the worst one, which is?
The adiabatic is the adiabatic because we compare with the adiabatic transition.
Okay, so it's not because I am confused. I know that they have been talking about this right now, but I don't listen. So, but it's fine. I mean, I am confused. Just this thinking. So the adiabatical thing that you explained, it's inside the VQE optimization, or it's
what
different?
I made that maybe is not good, but what I made is I use the adiabatic transition to calculate the CD term, and later the CD term what you have is a term like this G, and then you have the parameter that you change because you have this one and you change this lambda. And here you have lambda, you can see the structure and you make the shortcut. What happens that what I make is I don't care when I'm optimizing, I don't follow this lambda, I don't follow this G. I put a random parameter. I put a parameter that is what I will optimize. Follow again I only take from the adiabatic the structure of the ansatz later and optimize like a normal one.
Okay. Okay, I think I understand.
I have a couple of questions.
Okay.
So, yeah, so the adiabatic that you're talking about, that is the totalized evolution, right?
What? Repeat, please. I don't hear you.
So the adiabatic plot that you have plotted, which performs the worst, that is just totalized evolution, right?
Yeah, it's adiabatic.
4 steps.
I don't get it.
Okay, and what's the second one?
The second one is adiabatic with shortcut, and the other is the VQE.
Okay. So third one is the VQE, right? With
the good one. Yeah, the blue one is the VQE that arrives to the yellow line, to the exact value.
Okay, and what is the classical optimization for that? PSO?
What?
The classical optimization routine.
The classical. I repeat. The classical optimization of.
Which optimizer do you
I use gradient descent. I don't remember the optimization, but the PCO is other measurement that is not here. I make it, and what I ask before everybody comes is how I can, because my problem is I don't know how to compare the PCO with the gradient descent fairly, because you make a lot of, because how to compare it I think will be good if I make it a big system and one fails and the other don't fail. This will be the best one, and I'm waiting for this. But if I only use
PSO is a global optimization, right?
What?
So the method PSO is like there are two optimizations, right? The one is local. Local is gradient descent based method.
Yeah.
Another is a global optimization.
Yes.
PSO is one of the globals, right?
Yeah.
So you can compare it with, you cannot compare it with gradient descent. I think there is no way to compare it because it's another type of optimization.
Yeah. So my idea is.
You can compare it with Bayesian hopping or some other global optimization.
Yeah, I think the best way to compare it would be go to a complex system and not compare
And,
it.
Okay. And what is the size of the Hamiltonian? I mean, how many qubits do you use right now?
For this problem, for the hydrogen, it's only 2. For the lithium hydrogen, you can use 4. And from because then if you find because your Hamiltonian have a lot of terms, but you can reduce because there are some dummy rotation, and this is not necessary.
So right now it's 4 qubits without noise.
Without any the hydrogen one without any potentiation are 4 qubits, and you can make it in 2 qubits. The lithium hydrogen you can make it in 4 qubits. There is everything in everything tabled in a paper that because you have to. There is complex because you can reduce everything, but it's complex to make it like generalize this because there is some methods that they make to reduce the number of qubits you have to use in your circuit. There is a method and as Puru make it, but it's bad generalizes, so I have to read it much better because when I read it, he only worked for 3 molecules and I don't know how to generalize it to, for example, to a benzene molecule is what I'm making also. Reading this and see what happens there.
Okay, and what is the locality of the CD term that you use? I mean, is it 2-body? So the CD term that you use, right? I cannot see the screen.
It's 2-body.
What is the locality? So
2-body.
ZY plus YZ.
Yeah, 2-body.
Okay, cool. Yeah, so, yeah, I think that's, yeah, thanks.
Okay, so I think there is no more questions. So thanks for your attention. If you want to continue discussing, I'm there.